Okay, should we get started? All right, so the goal this week is to start finding some differential equations to describe the scale factor A of t. And based on what the universe looks like at a particular time, we have different behaviors for the scale factor. So today I want to derive what's called a Friedmann equation, which tells us how essentially the Hubble parameter evolves as a function of time. So by that differential equation for the Hubble parameter. And then as we proceed, we'll also provide the acceleration equation, the fluid equations, the stress equations of states, and finally we'll talk about the multiple constants. So before we get started, are there any questions from last week? So I think tomorrow we're having a tutorial on problems from last week, right? Okay. I've also posted lecture notes and the actual lectures as well. Okay, so recall from last week that we derived the L4W metric, or at least motivated it, we derived it explicitly. And the metric looks like this. Where d omega 2 is the metric on the round 2 sphere. So theta is between 0 and pi, and phi is between 0 and 2 pi. And as kappa depends upon the curvature, as kappa of r can be r sine r over r, r or r sinh r over r, where kappa is +1, the universe is positively curved, kappa is 0, the universe is flat, kappa is -1, the universe is negatively curved. And r describes the radius of curvature of the universe. And A of t is the scale factor. It tells us how big the universe is at a time t, and we normalize things so that A of today is 1. Okay, so that's what we derived and discussed last time. So now we notice that depending upon the curvature, the sum of the angles in a triangle, alpha, beta, and gamma, is pi plus the area over kappa times the area over r squared, where r is a parameter which describes radius of curvature. So for a negatively curved universe, the sum of the angles is less than pi, and for a positively curved universe, the sum of the angles is bigger than pi. So one thing you can imagine doing is just drawing a triangle, measuring the angles exactly as you can, summing them up, and seeing whether it's bigger than pi or smaller than pi. That's one way to determine whether the universe is positively curved or negatively curved. The problem is we can't draw a triangle big enough. Looking at terrestrial triangles, to the sensitivity of our instruments, the answer is going to be, the answer is going to be pi. If we're looking at, say, a triangle from Mars to the Earth to the Moon. We can imagine doing that, but we can't measure the angle sufficiently well to tell whether the universe has a positive or negative curvature. So we should do better in order to come up with determining what the curvature of the spatial sections are. So we'll try to infer this from some differential equations with a scale factor. Suppose the universe is positively curved. And it's positively curved, the spatial sections are sphere-like. Okay, so if we determine that the Hubble distance is c over h0, and this works out to 4,300 megaparsecs. So let's suppose that the universe is positively curved. This tells us there is a circle with a circumference c is equal to, we call it curly c, is 2 pi r. Okay? So if the universe is positively curved, and we're sitting here, we're seeing light from some galaxy, we should also see light from that galaxy after it makes a circuit around the universe. So we should see images of the same galaxy at distances x plus 2 pi r, x plus 4 pi r, etc. We don't see such images of the galaxy, which tells us that c times the speed of light is less than the circumference of the universe. Light hasn't made it around the universe within the lifetime of the universe in order that we see extra images if the universe is positively curved. Okay. So again, there's no obvious way of determining whether the universe is positively curved, which we would be able to do if the universe was, the circumference was small. Okay, so again, we need to do better. So I want to look at how you do better. So the Poisson equation tells us that the gravitational potential has a Laplacian, which is 4 pi g Newton times rho. I'm not going to derive this equation for you. I'm just going to take this as a starting point. Phi is the gravitational potential. And rho is mass density. So the energy density epsilon is rho c squared. So the acceleration due to gravity, so I'm working in a Newtonian language at the moment. The acceleration due to gravity is minus the gradient of the gravitational potential. So we know that the acceleration gives a 1 over r squared force law. So what does that tell us about the behavior of phi? How does phi scale with r? So we know the acceleration in Newtonian gravity scales like 1 over r squared. It's inverse square law for how gravity behaves. So if acceleration is minus the gradient of phi, how does phi behave with r?
It's 1 over r.
Yes, it's 1 over r. So the potential will scale like 1 over r. You already get a 1 over r squared force law. Okay, so we also saw last time, so this is Newtonian physics. In contrast to Newtonian physics, we had Einstein. And Einstein told us that there was a tensor we can define, g mu nu, which is called the Einstein tensor, which is a combination of the curvature and the metric. So r and r mu nu are derived or calculated from g mu nu. So this is the left-hand side of the Einstein equation to describe geometry. And the Einstein equation was that g mu nu is 8 pi g Newton over c to the fourth t mu nu, where t mu nu describes the magnitude. So the Einstein tensor is proportional to the stress energy tensor, according to the Einstein equations. So t mu nu, for our purposes, can be thought of as a diagonal matrix, rho c squared p P, where P is pressure. And this is again the energy density. Okay? So if we notice the energy density, this is rho c squared. This is mass per volume, so mass per length cubed, times c squared, which is length squared per time squared. So this is mass per length times time squared. Okay? So what's pressure defined as? Force per unit area. So this is so force is mass times acceleration. So it's mass length per time squared times area is 1 over length squared. So this is again mass per length times time squared. Okay, so the things which appear in the stress energy tensor, the pressure and energy density, have the same units as they should. Okay. In general, one of the secrets for doing, well, theoretical physics or physics in general is you can guess the right answer often on numeric factors just by working on the units. So it's useful to be familiar with what units things have. Oftentimes it gets you to most of the answer without much work. Okay. So the Friedmann equation, the equation we're after now, links the scale factor A of t with the curvature parameters, kappa and r, and the energy density, epsilon of t. The energy density can change the function of time, and it will change the function of time because the density and the universe's volume is changing as a function of time. Yeah?
So shouldn't the R also be changing as a function of time if the universe is expanding?
No, the R is just a curvature of the spatial section in co-moving units. So when we're co-moving units, the same position was kept, but the universe is expanding. There's a scale factor in front of the co-moving coordinates. Okay, so what I'm going to do is I'm going to give you a Newtonian derivation of this. So the Newtonian derivation, I'll admit, from the beginning, is cheating. The proper way to do this is to use the Einstein equation, but the Newtonian derivation gets us close enough and we can fix the answer, because we know the answer, at least some of us know the answer from the Einstein equation. Okay?
So we derive it properly in honors.
If you're taking general relativity, then yes, you'll see it properly in honors. Okay, so in this Newtonian derivation, we're going to consider a homogeneous sphere of radius r sphere, and it's going to have a total mass m sphere, and this is going to be constant in time. Okay, so you've got some sphere of mass ms, and its radius can be a function of time. Okay, so we'll place a test mass. This is our sphere, radius rs. This is test mass, little m, on the surface of the sphere. Okay, so that's our setup. The force is going to be minus g Newton, m sphere, m of the test mass, over radius of the sphere squared, directed radially, and this equals mass times acceleration. So the acceleration is going to be d squared rs dt squared, which equals minus g Newton ms rs of t squared. Okay. So let's take this equation and multiply both sides by drs dt. Okay, so I'm going to call drs dt rs dot. I'm going to call the acceleration rs double dot. So we have rs dot, rs double dot equals minus g Newton ms over r squared, rs dot. Okay. So now we can integrate this equation. So we integrate this equation. We have 1/2 rs dot squared equals g Newton ms over rs of t plus some integration constant u. Okay, so if you take derivative of this side, you get the 2 equivalent to 1/2 rs dot, rs double dot. If you differentiate this side, you get minus gn ms over rs squared times rs dot. Okay, so this is the right integration of this equation. Everyone happy with that? Okay, so we have 1/2 rs dot squared plus g Newton ms rs of t equals u, which is a constant. Okay, so this is the kinetic energy per unit mass, and this is the potential energy per unit mass.
So,
Yeah.
so what were you integrating in the second line with respect to what?
Integrating with respect to t.
Okay.
So, total mass ms is 4 pi over 3 rho of t rs of t cubed. So 4 pi over 3 rs of t cubed is just the volume of the sphere. Just the volume of the sphere times the mass density. Okay? So we assume the expansion or contraction of the sphere is isotropic, which tells us we can write rs of t as rs times a of t. So rs here is the co-moving radius. So now, just plug this in to the equation we derived. So we have 1/2 rs squared a dot squared equals g Newton over rs times a times the expression for ms, which is 4/3 pi rho t rs cubed a cubed plus u. And let's divide this expression by rs squared a squared over 2. This gives us a dot squared over a squared equals 8 pi g Newton over 3 rho of t plus 2u rs squared a squared. Okay? So here, this rs and this a cancel the exponent and lower it to a 2. Okay? So, we see this expression only a dot squared and a squared. So the left-hand side is positive. Now, for a contracting sphere, a dot is less than 0, so this is the reversal of an expanding sphere. Where a dot is bigger than 0. Okay, so now we're going to study this equation in various cases. The 3 cases corresponding to whether u is positive, u is negative, or u is 0. Okay? Yeah.
So can you say again what you mean by constructing sphere and a dot less than 0?
Okay, so this equation only has a dot squared and a squared appearing in it. So the sign of a dot is washed out when you take the square. So suppose a dot was less than 0, then our sphere would be contracted. That's basically a time reversal of an expanding sphere. So you can just take the solution right now it's expanding, and if you want to consider the contracting one, just put a sign in front. Okay? The 3 cases, roughly speaking, correspond to what happens when you launch a rocket. I'll explain what I mean by that momentarily.
So that would be an equation.
This equation is almost a free-bit equation. It's a Newtonian free-bit equation. Okay, so case 1, u is positive. So if u is positive, the mass density is always positive, so the right-hand side is positive. So this means that a dot squared is always positive. So the expansion doesn't stop. Okay. Case 2, u is less than 0. So the right-hand side is 8 pi g Newton over 3 rho of t plus 2u over rs squared 1 over a squared. So this, if you express this in terms of mass again, is 2 g Newton, mass of the sphere rs cubed over a cubed, plus 2u rs squared over a squared. And this guy can equal 0 if this negative term here exactly cancels this positive term here. Okay? So equals 0 if a achieves a maximum, which is minus g Newton ms over u rs. So the expansion here stops at a max. And we have the equation d squared rs dt squared equals rs a double dot, which equals minus g Newton ns over rs squared a squared, and this guy is less than 0. So once it reaches a maximum, the sphere then contracts. So the sphere expands out to a maximum size, and then it contracts. Case 3 is when u equals 0. And in this case, a dot goes to 0 as t goes to infinity. So these 3 cases are, roughly speaking, what happens when you launch a rocket from the Earth. If a rocket has an escape velocity, has a velocity as big as the escape velocity, the rocket keeps going out forever. If the rocket has a velocity just smaller than the escape velocity, it reaches the maximum height, and then it falls back to the Earth. And if the rocket has exactly the escape velocity, its speed goes to 0 as time goes to infinity. Okay, so this is a Newtonian derivation. What are the reasons to be suspicious of this? Why should you believe none of this? Even though it's almost the right answer. So what assumptions go into cosmology? What?
The Copernican principle?
Okay, Copernican principle, homogeneity and isotropy. Is our assumption that we are living in a sphere consistent with homogeneity and isotropy? Why?
I guess if you're on the tip of the sphere, it might be.
It says you're on the tip of the sphere, though. You've got a volume that's occupying space. It's a volume. So there's a special point in the sphere. There's a center of the sphere. So not all points are the same in the universe. There's a special point in the center of the sphere. Similarly, not all directions are the same. There's a direction towards the center of the sphere. So as a result, the assumptions we've made for this universe are inconsistent with the usual assumptions we need to make, namely homogeneity and isotropy. That's one reason we're suspicious of this calculation. You might say that the sphere is just cut out of a homogeneous and isotropic space. Just take some sphere which is embedded in a homogeneous medium set. What's the problem with that assumption? Well, we know that what happens to gravitational force inside a spherical shell?
Should be 0.
It's 0. So inside the sphere, there's a 0 gravitational force. So that's also, not consistent with the assumptions we've made here. Okay. So in essence, we need to come up with a proper derivation. The proper derivation is unfortunately beyond the scope of this course. So I'll just tell you how you fix the phase treatment equation in order to get the real one. So this is a phase equation. And the real equation is going to be a dot squared over a squared equals 8 pi g Newton over 3c squared at quantity. Okay, so the first term is correct. You just multiply and divide by c squared. Rho c squared is the energy density, so this term matches. And the other term is going to be minus kappa c squared r 0 squared 1 over AOT squared. It's called r squared, so let's stick to that. So this equation is a pretty good equation.
So sorry, what was the epsilon? Oh, that was the energy density, sorry.
Yeah. Okay, so remember that Einstein told us in special relativity that the energy is m squared c to the fourth plus p squared c squared square rooted. So in the non-relativistic case, where the velocity is much, much less than the speed of light, the momentum is approximately mv. So we can write the energy as mc squared of the square root 1 plus v squared over c squared. And this is approximately, using Taylor's theorem, mc squared plus 1/2 mv squared. So the kinetic energy plus the rest mass energy of the particle. So epsilon, since v is small, epsilon, the energy density, is approximately rho c squared, with small corrections that come from the kinetic energy. Okay, so that's a non-relativistic case. In the relativistic case, so let me erase the Friedmann equation. In the relativistic case, we have the energy equals P times C. So for example, for photons, this is going to be Planck's constant times the frequency. And these photons, for example, contribute to epsilon and therefore to the shape of the universe. So the way that non-relativistic matter and relativistic stuff like photons contribute is going to be different. And we'll see maybe next time what this difference is in terms of the equation and state. Okay, so we notice the first term of the Friedmann equation matched the fake Friedmann equation. But the second term, we set 2u over rs squared to minus kappa c squared over r0 squared. So kappa is related to the Newtonian energy, u of the test mass, and u less than 0 corresponds to kappa equals +1. U bigger than 0 corresponds to kappa equals -1, and u equals 0 predictably corresponds to kappa equals 0. And we'll see what this means as well. Okay? Okay, so we notice the Friedmann equation involves a dot over a squared, and this is of course the same as h of t squared. So we remember from last time that velocity is the rate of change of a proper distance, and this equals dt of t times h of t. So this is how the proper distance then is related to the Friedmann equation. We have h of t squared equals 8 pi Newton over 3 c squared epsilon t minus kappa c squared over r squared a squared. And H0, the Hubble constant today, is about 70 kilometers per second per megaparsec. So H0 squared is equal to 8 pi g Newton over 3 c squared epsilon 0 minus kappa c squared over r squared. So if we can measure the energy density today, we can measure H0 today, we can sort of figure out what kappa is, or the ratio of kappa over r squared is. Okay. So that addresses one of our confusions. Let's assume momentarily the kappa is equal to 0, so we have spatially flat sections. Then h of t squared equals 8 pi g Newton over 3 c squared epsilon of t. We can use this to define a critical energy density. Epsilon critical of t is 3c squared over 8 pi g Newton h of t squared. So this is the critical energy density. I'll show you what critical means. So if epsilon of t is bigger than epsilon critical of t, then h of t squared equals 8 pi g Newton over 3 c squared epsilon critical of t plus whatever the difference is between epsilon and epsilon critical minus kappa c squared over r squared a squared. So plugging in for epsilon critical, this value here, we see that we see that 0, we can show that 0 is equal to delta epsilon minus kappa c squared over r squared a squared. So this implies then that kappa is plus 1, because this is positive, c squared over r squared a squared is positive, so kappa has to be plus in order for these terms to cancel. Okay?
So
Yeah.
what did the a squared come from?
There's a 1 over a squared in the frequent equation.
Oh,
Which should be a But this is a 0 squared, which is 1. That's why I thought. So we looked at the case where epsilon is bigger than epsilon critical. What about the case where epsilon is smaller than epsilon critical? If epsilon is smaller than epsilon critical, we can similarly conclude the kappa is minus 1. So computing the energy density, comparing the critical energy density, gives us the sign of kappa. So, epsilon critical today is equal to 3c squared over 8 pi g Newton, h0 squared. And this works out to 5,200 MeV per c squared, per meter cubed, sorry. And rho critical is epsilon critical divided by c squared, and this is 1.4 times 10 to the 11 solar masses per megaparsec cubed. And those units are incomprehensible to anyone because who knows how many solar masses there are per cubic megaparsec. But anyway, that's the mean. It turns out the mean density of the universe is close to the critical density. Meaning the universe is very nearly flat. So we still don't know the sign of kappa yet. Okay? Yeah.
So it's just about flat. Why can't we just say kappa as 0?
Because it turns out kappa matters. It determines the fate of the universe. Does the universe contract? Does the universe expand forever? That's determined by kappa. Just like the escape velocity matters. We can also define a quantity called omega of t. Omega of t is the ratio of epsilon of t to the critical energy density, epsilon critical of t. And in terms of the Friedmann equation, we can write the Friedmann equation as 1 minus omega of t, maybe I'll have you do this in the tutorial, minus kappa c squared over r squared a squared h of t squared. So the thing to notice here is that the right-hand side can't change sign. So a squared is positive, r squared is positive, h of t squared is positive. So if kappa turns out to be negative initially, the sign stays negative throughout the history of the universe. The sign on the right-hand side can't change. This tells us that 1 minus omega of t also has a sign that can't change. Either omega is bigger than 1 or omega is less than 1 for all time. So today, kappa over r squared equals h0 squared over c squared 1 minus omega. Again, if you measure omega today, omega 0, you find something very, very close to 1. Yeah.
Is that because of we just don't have instruments sensitive enough to pick up the curvature, or is that?
I think when we discuss, we'll answer that in a few weeks.
Okay.
Okay. We're going to measure the cosmic microwave background. The cosmic microwave background is sort of a 3 Kelvin bath that the universe sits in. And the behavior of that 3 Kelvin bath is what lets us deduce how close we are to 1 here. Okay. So we'll get to that. Okay, any questions? Okay, so next time we'll derive the acceleration equation, namely the behavior of A double dot over A. And we'll see that there's a other equation you can construct out of the acceleration equation and Friedmann equation called the fluid equation, which will sometimes be more convenient. And it turns out the fluid equation leads us to a discussion of the equation for the state. And one of the things the universe is made of is the vacuum energy density. It turns out the vacuum energy density has negative pressure, and we'll explain what that means. And we'll show that negative pressure is what's going to explain the expansion of the universe today. So that's where we're headed. Okay, so I'll see you on Thursday morning.